Yep, welcome. So today we'll be talking about the numerical solutions of the wave equation. So to illustrate, numerical solutions of the wave equation, EQN. So the 1D wave equation looks like UTT equals C squared UXX, where this is the twice time derivative or the acceleration. This is the C is the speed of the waves in the medium, and UXX is a twice spatial derivative. So first I will try to motivate this formula using some physical derivations. So we will base ourselves on Hooke's law, which should be known. So Hooke's law, which we should all be familiar with, is force equals some kind of constant and the displacement. I guess this is all vectors. And also conservation of mass. Meaning that we don't really want any mass to be lost in our system. So all the mass has to be conserved. So if you first imagine a stretch like string, so we have one point there to the left and one to the right, and then you have your string stretched between these two, like so. So in our example, the endpoints will be stationary, and then the string is left to freely vibrate. So it can also vibrate up and down, like so. And we'll also assume that this is perfect, elastic, and a uniform. So it will be like basically a perfect string. No inhomogeneities and nothing to worry about. So a better sketch of this would be. So here we have a string. Let's see. This is the placement. This is U. This is the displacement of the string, so how much the string moves. And then we have the position, X over there. So a string will be of length L, start with 0, and we will look at one simple mode of it right now. Should go something like this. Then we will have some forces on the string. We'll have something going this way with let's call it alpha, and then over here we'll have a force T2 at an angle beta, and this is at position X and X plus delta X. I think I've gotten all the details. So you can imagine that all the particles on the string, they can move in the vertical direction. So only up and down. They can't move side to side. So only up and down right now. So since it's only moving up and down, there will be no horizontal movement. So no horizontal movement. Reason. Movement. This means that the sum of forces in horizontal direction should be 0. Let's see, did I... Yes. So it can't move like this, it's only moving up and down. So when we sum forces going left and right, they should be 0. This means that the forces acting horizontally here are minus T1 cosine of alpha and plus T2 cosine of beta. This is because this force acts to the left and this force acts to the right. So this gives us this component. Yep. And this means that if you sum these forces, so if you have T1, so you see since they are in opposite directions, they will be 0, but if you sum them, see cosine of alpha, these should be the same, so we just call this force T. It's T, which is constant. So this is in the horizontal direction. So in the vertical direction, we will have that, well, Newton 2, sum of all forces acting, let's see, sin of beta minus T1, sin of alpha should be the mass of the string times its acceleration. And this will just give us the density times our element, so that's just this element here. So this string has a density rho and also length delta x. And this has an acceleration a, which is the twice time derivative of the displacement. So this will be in the horizontal forces, and this is vertical forces. Like so. I need a better. There we go. So then we can simply divide these by each other. That should be perfectly possible. So we divide this one by the force T. So T2 of sin beta minus T1 sin alpha divided by the force. So like one of these are the same. This will give us T2 sine beta divided by T. Well, we can substitute this force T because it's constant. So in this case, we will have T2 of cosine of beta. And this time we will have sin of alpha times T1. Oh, cosine of alpha, and this should be, well, the same as this, only divided by a force, rho delta x, or this T, U, T, T. Does that make sense? So we've just seen that the force is acting on this system right now, and then we've decided that we want to just take the forces acting in the vertical direction and divide them by one of the forces acting here. So either this force or this force, but they are the same because of the horizontal movement restriction, then the sum of the forces should be 0, so we can just substitute them. So if we try more here, we see that these two cancel, and sine divided by cos is the tangent. So we will end up with the tangent of beta minus the tangent of alpha, so delta x over t u t t, like so. And then we're going to look at the derivative. So the tangent can actually give us the derivative in each of the points. So if this makes sense. So you have some kind of force or movement this direction, and then this direction, and then this will be the tangent. And that should give you the derivative in that point. So to write this more mathematically, we have that. I'm going to use this area. So we have that the tangent of alpha equals du dx at the point x, and the tangent of beta will be du dx at this other point. So this one actually gives us the derivative. So the tangent of this angle will actually give us the derivative, the displacement derivative in that direction. That is pretty neat. So by just using this, we see that we have dx u at the position x minus the spatial derivative at the next point. And we will get, let me see, so I don't do anything stupid, delta x over t u t t yes, and then you see if you just divide by this delta x. Yes, they are. If it's like, yes, they are. So the first one here is the this one. I just messed up the subscripts. That's all. So, and then we just divide by this, and then you will see that this looks eerily familiar as the twice derivative. Delta x. So this will be basically u derived at the point x plus delta x minus u at x equals rho. That's it. Equals rho over t u t t. And then if you're with, oh well, this is going to be the derivative as well. So if you take the derivative of the derivative, then you have, well, twice derivative. So this construct here is going to be u x in a discretized version. So to sum this up, we will have t over rho u x equals u t t, or if you can write it more succinctly, c squared, where c squared equals t over rho. And c is the speed of the wave in this video. So or the phase velocity, I guess, is the most accurate. Any questions? Does it make sense? Is any step? I guess some steps should be, well, you have to think about them. Yes? Hmm? Oh, this T.
I know, but this U, what prepared?
But oh, U is the displacement of the string. Yeah, so if you go back here again, you see I briefly mentioned that U is the displacement of the string, so how like big of a wave you have, or the amplitude of the wave. So which was fairly neat. And then this also generalizes in higher dimensions. So you'll see well, this is called the acoustic wave equation. So if you want it in 3 dimensions, well, you can just add more of these terms. So this is the twice derivative in x, and then you have the twice derivative in y, and the twice derivative in z as well. All of them times c squared. Some of you might want to work with this and at the project. We'll be looking at the wave equation for one of the tasks, problems, and the other one we will look at the diffusion equation. So you have to pick one of those. Can I remove this as well? Guess I don't need it. So then, since this is numerics, we will look at the discrete version of this equation, or the differential form. So again, we will have u t t at some position x at time t, c squared u x x at position t. So this is our partial differential equation. X will be from 0 to the length of our string, and t will go from 0 to the end time big T, or yes, big T. So this T is the same as this T. I could have just picked a different constant, I see. I first had tau, but that's a truncation error. Let's just say that the time t goes from 0 to big T. Then we will have some boundary conditions. So we have at the endpoint 0, t should always be equal to 0. U of L t 0 for all t inside our interval from 0 to t. We'll also have an initial condition or initial state of the string. So at every position x, we'll have some function defining the state of the string for all x inside 0 to L. And we also need the first time derivative, so ut of x0 is defined by some function g of x for all x inside the same interval, like so. And to make this complete, we will also define a region. which is, well, x of t, so time and space, given that x is inside this, and 0 t t. So I'll illustrate how this looks like after having some more space. Yep. So our region R just bounded, so we have L over here, 0, the length, and then time moves up. This is T. So then we have discretized of space, so we will have, see, I can use some kind of color for this. We'll have different points along this axis. Let's say that this is a T tall. Last one, and then we have a spacing. Spacing here will be delta T, and spacing here is delta X. So we will have that, well, xi equals I times delta X, and Tj equals J times delta T. If this is at xi, then this point is xi plus 1. This point is xi minus 1. This point here is tj minus 1, and up here tj plus 1. So the next time step, basically. Yep. And then the point over here, this will be u of 0 t, going all the way up here. And this will be the boundary condition u of L t. So here you have one boundary condition, and here you have, well, kind of crooked, but guess you get the picture. So you should have seen this before, I hope. Just the numerical, well, stencil, which we'll come to later. So I want to kind of keep it. And then we'll just use central differentiation operations or operators in both time and space. If you want a more accurate wave equation, you can use different differentiation operators, so with bigger step length and whatnot. But we'll just keep it pretty basic here. There we go. So again, UTT at xi tj equals I j plus 1. I guess you're as bored as me in writing these indices. I j minus 1 divided by delta t squared minus delta t of 2 for factorial dt4 u at x I u j should be inside the interval t j minus 1 to t j plus 1, like so. And then in a very similar fashion, we have the twice spatial derivative at xi, tj I plus 1 times j minus 2 ui j plus ui minus 1 times j delta x squared minus delta x squared 4 factorial dx 4 of chi I at tj and chi I is, well, I guess you've guessed it, like so. There's a lot of decoration going on. It's number 2. And then we can insert this into the wave equation. So basically just do a substitution. And you'll see that we get j plus 1. You are very allowed to take pictures of this instead of writing it. J minus 1 I minus c squared u plus 1 plus 2 ui j plus ui minus 1 j over delta x squared, and then we move the arrow terms to the right hand side and we end up with 1 over 12 dt squared d, well, let's see, dt power 4 u minus delta x squared dx power 4 u, like so. And then we can see that the local truncation error kind of, well, basically just falls out. But yeah, I can just briefly mention it. Local trunk error, or LTE.
Sorry, was it supposed to be like 24 instead of 12?
Yes, guess it should, but I think, yeah, because 4 factorial, that is 24 and not 12. But do I have more of them? No, I don't. Could be I've just done a mistake here. Yeah, I think it's going to be 24. 4 factorial. Unless I made... Yeah, that makes perfect sense. It should be... Yeah, there's something wrong in my notes. Apologize. Up. But then I have to think about a local truncation error. I guess that's wrong as well. Well, equals 124 delta t squared for u squared dx for and u. So basically it's O delta t. So it's second order in both space and time. That's at least the point here. I was trying to figure out, is there a reason why I've said 12 instead of 24? I don't think so. Anyway, 4 factorial equals 24. Yeah. But yes, if we now next neglect the error term, because if we were to calculate the error term for each time step, then why shouldn't we just use it in our estimation as well? So, well, we just ignore it or neglect it. Then we can solve this for the next time step, and we will get ij plus 1 minus 2u ij plus u ij minus 1 equals c squared delta t squared over delta x squared. And since we'll be using this a lot, I'll call this r squared. So this is different from the one we had last lecture, different r. It's just like constants. I plus 1, I j, I minus 1, j, like so. Solving for the next time, we see that we get, I'm going to skip a small step here, equals 2i minus r squared u I j plus r squared u I plus 1 j plus u minus 1 j minus u I j minus 1, like so. And then we can go back to our stencil. So I won't weigh all of the points, but just, well, point out which one we are using. So if we want to estimate this point up here, we can look at our stencil. So this is going to be our u j plus 1 I. Then we see that we need these three. So these are our spatial points in order to figure out the derivative there. And then we need this point. So this is going to be a stencil. Ij plus, plus 1 j minus 1 j and u I j minus 1. So see, we need to go further back in time as compared with the other stencil. And then following a tradition, we can write this on a matrix form. So again, we have, if we take, I'm just going to do everything over here. Is this okay? Can I
think it's supposed to be 12.
You think so?
That's the coefficient of second derivative.
Yes.
2 factorial.
Yes.
I think it's oh yeah.
Yes. That makes sense. So it's supposed to be so 2 something like this. Yes? Yes. Okay, so this was the error then. My apologies. Yeah, there should have been a 2 up there. Then I just have to let this wait. Did all of you catch that? So I forgot a number here, and it propagates through all of the thing here, all of the equations. It's not really that important, not yet anyway, since the most important bit is just this. So how it scales with the grid spacing. That is the most important bit to know. Can I? Yeah. So next, if you organize all of our grid in a neat row, as basically you can just use this. So we get a U, which looks like, well, if this is going to be times of J, 0, J, J, and U, it's going to be N and J over there. So this is basically just all of these vectors down here squared. And then, looking at this, we can construct an A matrix, which will look something like 2 of all squared, all squared, all squared. So see, this is also going to be a tri-diagonal sparse matrix. And then can be easily solved using, for instance, conjugate gradient. 2, 1 minus r squared, squared, 0, 0, 0, 0, and this 0 down there. See, 2, 1 minus r squared, squared. I guess r squared here as well. Squared. 2, 1 minus r squared. Zeros all over the place. Like so. So this is going to be a matrix. And then you see we can, by using these two matrices, we can easily state the equation as, well, in matrix form anyway, U of j plus 1 equals a j minus of j minus 1. Yes. So see, we need both at the previous and, well, if we want to calculate the next time step, we both need a current one and the previous ones. So we have a problem when we want to start here. So when we're starting, we don't know the 0. Well, it depends on how we start. So if we start at time t1, then we don't know the value at, I mean, if I can illustrate this. So the problem is we don't know the value of the displacement at these times here, because they're also our domain. So this is R. R is like, yeah. As I said earlier, this is R. So we have to figure out a way in order to estimate this point as well, so we can actually kickstart our simulation or solution of the wave equation, if you want to call it that. And how can we do this? There are two tricks. So first we'll do a naive approach. And that is that, well, we can assume that it's given by the initial conditions. So remember I said that mu of t 0 g of x. So that's one of my initial conditions or boundary conditions. So this is the just one-time derivative. So we can basically replace this. So we will have of 1 I minus position I of 0 delta t 0, which means that of I 0 plus delta t this g of x. So this is basically just solving this here and knowing that we have this as an initial condition and just using this. Though there's a problem here because this is only first order in space, so time, sorry. So the problem here this is only OT. So first order in time. And then I think it might be a good time to stop and show the better solution after the break.